Hello, welcome to numerical ship and offshore hydrodynamics. Today we are going to discuss some basics of the boundary element method or panel method. Okay. These are the keywords that you have to press in order to get this lecture. Okay. So, let us start here. So, in last class I just typed these words like in panel method we divided the domain of definition or boundary either by the big patches or by the smaller quadrilateral or triangular panel, right. But we really did not realize what I try to say. So, today we very carefully try to understand these statements. Okay. Now, when I say that this panel method we divide the domain of definition or the boundary. So, what does that mean? So, now let us see when we start with this boundary integral equation method, we start with the equation which is phi p, right, and you just if you want you can multiply it by the alpha p. Okay. This equals to with some boundary, right, some boundary. So, I just called S b, b stands for the boundary. So, some boundary and then it is phi and then you can see that I just write here q, right, and then I write del g del n and then g also I write as p comma q, right, and then minus it is g p comma q and then multiply by the del phi del n and I called here as q and then I integrate over this surface. Now, this is the integral equation that you are going to solve for this panel method. Now, very important that we need to discretize this boundary. Okay. Now, if I see if I try to draw a let us say a two dimensional boundaries. So, we discuss this is my boundary and then maybe the top part we can see that there is maybe you can consider these some waves are there, right, and then in this waves you can put some body also here and we can say that this is basically my non-linear boundary, non-linear free surface and this is my linear free surface. So, we understand this. Now, also we can call this as S infinity you can say because S minus infinity in fact you can call as S minus infinity, you can call as S infinity and this you can call the bottom or you can say just I say just BOT bottom. Now, here this S B stands for all these boundaries. Now, here we need to discretize the whole boundary, right. However, based on the choice of these Green's functions, based on the again I repeat based on the choice of the Green's function, sometimes we only need to discretize the free surface and the body or sometimes we need to discretize the body. If you remember in last class I said some mesh A1, some mesh A2. In mesh A1 we have to discretize only the body. In case of a mesh A2 we need to discretize not only the body, but also the free surface. So, what happened finally we have to either we need to model the free surface let us say and the boundary or we need to model only the body without the free surface. So, when I talked about this S B, so basically we are trying to say that we need to discretize either this whole thing or we need to discretize this one. right. Now, in case of a two dimensional problem, this is simply a straight line. You can or you can take is a curved line also, based on the fact that you are trying to do the higher order or lower order whatever. But essentially what you need is you need to discretize the, okay, let me do it in yellow. So, you need to discretize this free surface by some small lines like this. So, these are the your weighted surface, because I really do not want anything above the water. So, I can leave the top part of this body and then this one, right, or you have to discretize only the this body. Now, this is in case of a 2D, but in case of 3D it becomes a surface. So, we can assume that, let me draw a surface like this. So, just draw a small 3 dimensional fill, something like this, and then you can draw some kind of a surface like this, and you can consider this as your free surface. So, then you have to discretize or you have to mesh the whole free surface, and as well as you need to discretize the body. So, you can see that though it is a very bad grade, but just try to understand the concept. What I say that in this case you need to discretize the not only the body, but also the surrounding free surface. Fine. Now, how you are discretizing this body as well as the free surface? Now, there are a lot of options are available. Now, if I try to do this with lower order panel method, which is more popular, if you try to do it with the lower order panel method, then actually you are discretizing this whole domain using some sort of quadrilateral. So, we cannot say it should be typically the rectangle, it is not possible, right, because you can see this part actually you really can't do some rectangular stuff, right. So, maybe you have to do. So, now even if I discretize like this way, some sectional lines, these are some sectional lines as I mentioned. So, I can draw some section lines. So, this since it is symmetric. So, you can only one part you can mesh and you can define that is symmetric. So, other part can automatically one can take care, and then this is you can see is the water line. Now, you see here what I did is as follows. I am making some small quadrilateral, right, and therefore, I discretize. So, this S B, the whole discretization, let us take this method A 1 only, where you need to discretize only the body. Let us take that, let us go with this. So, then what you need to do is this S B, you can see it is sum of this small areas S I. So, finally, I understand what is the meaning of the discretization. It is this domain, this computational domain I discretize by some small areas S I or quadrilaterals. Sometimes in, let us say, in this situation you might have some rectangular panels also, because this corner part you can't handle nicely with this quadrilateral. Suppose if you try to do the quadrilateral, is become so thin like this. So, instead of doing this you can assume that to be an triangle. So, therefore, this S I should be the combination of any type of quadrilateral, not any type of, certainly like we have to take care many aspects that we are going to discuss in coming days, or it could be some kind of triangular. Now, unlike like CFD, normally they can do some hexagonal mesh also, but here normally we do not do that, either we go with the quadrilateral or we go with the triangle. Okay. So, when I talked about the first part, so now it is clear when I say that we divide the domain of definition or boundary either by, okay, now big patches I missed, okay, let us go back again to see that what is the meaning of the big patches. Now, instead of this, for example, we try to draw a circle. Now, how we can draw circle numerically? Though it is not a perfect circle, but how we can do that numerically? What you can do is, you can take very small segment, right. You can take very small segment here, and then you can approximate this joining these two segment by a straight line. Now, if this segment are small enough, so at least visually you cannot make out that whether it is a circle or it is a polygon. However, you can still draw this circle numerically using some quadratic function or cubic function, anything with a big patches. So, this big patch may be some, let us say some cubic function, it is let us say a x cube plus b x square plus c x plus d, something like this. So, similarly this one, this one, this one, this one. So, instead of straight line which is y equal to m x plus c, right, just let me write bigger way, instead of y equal to m x plus c, you are using some higher order function y equal to some a x square plus b x plus c x plus d, something like this. So, this is the difference between the big patches and the small segment. So, when you approximate by a straight line, then you have to take this segment is really small, so that visually you cannot make out that whether this one is circular or polynomial. However, in case if you ask for the higher order functions, then the same thing you can draw with the lower number of panels. So, segment may be lower because you are right, it already take care about the curvature part, right. So, this is what we say when you talked about the big patches. Okay. Now, second part is we assume the velocity potentials are either constant or linearly varying or any higher higher order functions over the panels. Now, what is the meaning of this? So, now let us try to understand when I say that the velocity potentials are either constant or linearly varying function or any other higher functions. Okay. So, again let us go back here and let us try to find out what is the meaning of the when I say that phi, we assume the distribution of the phi either constant or linearly varying function or higher order function. What is the meaning of that? Now, if you remember that last class when I talked about that to find out the flow past a cylinder, and we put here a dipole, right. And that means that we claim that if we put a singular function instead of the body, so you can have the same effect as if there is a body, right. Because we replace, see we really do not put any cylinder when we talked about the flow past the cylinder. We replace this cylinder and then place a dipole in there, right. So, this is the idea, and then we argue that in case of a ship also, if I try to find out the the velocity potential over a ship, then instead of the ship I replace the ship with some either some source function. So, let me write in this way, either some source or some dipole or maybe the combination of both. So, that was the argument. Now, let us go with this method A1. In method A1, we need to find out this problem and then we discretize my body, right. And then how do I get the phi over here? Now, if you look at this integral equation, let me write over again. The integral equation, this phi p is equals to this over this S b, right, and then you have phi q into del g del n minus del phi del n into g, and then you have to integrate over S in dsp. Now, see here I discretize the body, definitely I discretize the body. So, I understand that how I discretize the body is the summation of S I. So, I discretize the body. Now, we need to find out then in this discretization how phi is varying, right. Now, you see here the value of phi cannot be same the value of the phi here. Similarly, the phi is varying different value in this panel also. This phi has different value in this panel also. So, then how we can understand that how this phi is varying and actually how I can approximate the value of phi over here. Okay. Now, the popular way of doing it, we assume that for each panel the value of phi is different. Now, if you assume in this yellow one the value of phi, let us say phi 1, and maybe the red one the value of phi may be phi 2, and again in the blue one that value of phi may be some phi 3, and let us shaded something in green, this one, this green, then value of phi here may be phi 4. Now, remembering this choice of phi 1, phi 2, phi 3, phi 4, it is arbitrary, can be arbitrary, okay. Not necessarily this phi 1, phi 2, phi 3, phi 4 should be in order. When I call should be in order, I mean that not necessarily that phi 1 may be here, then this may be phi 2, this may be phi 3. So, I mean this all this phi are arranged in column fashion or all the phi may be arranged in the row fashion, no, not required. So, it the choice of phi may be arbitrary, but what I say is this phi is constant over a panel. So, what I say here as follows, I say this value of phi I is constant for this panel S I. Okay. So, it means that this phi also I can say that this phi also the summation of some small phi I, and this phi basically this phi is constant over some area, but the different from the different area. What is the meaning of that? Very simple. This is my ship. Now, I just do this for the 2 dimensional, like you understand, right. This is the patch, just do the profile view, let us say. So, what I call this value of this phi 1, it is only associated with the area S 1. So, over this phi I mean sorry, over this area, this phi 1 is constant. So, you understand this, right. However, just next area let us take now let us make it in order. Okay. So, now maybe this one is basically that second area S 2 and then this value for here maybe it is called as phi 2. Now, this phi 1 is not equal to phi 2. However, here in whole area S 1 everywhere the velocity potential is phi 1 and this is called constant panel method. It means that for a particular area phi is constant, for the different area phi is different. Okay. That means, for one panel the throughout the panel the phi is same, for the different panel phi is different. Then one can ask, I mean normally people ask at this particular point, then what happened in the boundary? What is happening in the boundary, which is very valid question, right. Because in this boundary, let us say this side I have phi 3 and let us say this side I have phi 4, then what happened to the boundary? We accept that in the boundary we have a discontinuity, because in the left hand side we have phi 3, in the right hand side we have phi 4. So, in this boundary definitely there will be discontinuity. Again second level of approximation is as follows. We claim that even if there is a discontinuity, it is marginal or it is ignorable. So, we ignore this discontinuity. But if somebody is very sincere and if he says that no, I do not allow the discontinuity in this boundary, then they can assume, let us take in S 1 area, this definition of phi may be definition of phi 1, that may be some a 1 some linear function, some a 1 plus some m m x kind of thing, some linear functions. So, and then maybe the phi 2 equal to some a 2 so it is m 1 x, it is some linear function m 2 x, something like this. So, then what, by doing this you can avoid the discontinuity at the at this boundary, because this is also linear, this is also linear. So, if I see closely, let us say there are 3 panel and if you assume this variation of phi is linear, so you can say that it may be something like this, and then you can make sure that this part would be the continuous. Okay. So, this also considered as lower order panel method, when either we can assume phi is constant or we can assume phi is linear. Now, suppose still you are not happy and then you can say that no, I want this phi to be the quadratic function. So, it should be some a x square plus b x plus c, something like this. Okay. So, therefore, at this point there is it is absolutely a nice thing. Let us absolutely there is no question of the discontinuity at the boundaries at this particular in this case. So, this called as higher order panel method. Okay. So, now it is very clear, in case of a lower order panel method we assume that phi to be constant and at least linearly varying, but if it is a higher order function, some cubic function, some quadratic function, many people takes this as B spline function also. In that case we called this panel method is higher order panel method, but in this particular course we are doing with the lower order panel method, and therefore, we assume this phi to be constant of a panel, I mean same panel and different for the different panel. So, now let us coming in the third point. Now, this third point again we need some more time to understand this. Based on the above assumptions, one can convert the integral equation into algebraic equation in the form of a phi equal to b. So, this needs some more time to realize. Okay. Now as I mentioned that classification of the panel method, they can divide into two part. Now, the second part we understand what is called the lower order panel method and what is called the higher order panel method, and then in the right hand side is basically based on your choice of the Green's function. As I said that we can take many type of Green's function to solve the same problem. Okay. Now, here very briefly let me explain that when I call that different type of Green's function, what is actually this Rankine. If you talked about this Rankine, the Rankine Green's function, we take this G, the Green's function, this equals to some 1 upon R, something like this. So, this is called the Rankine. Now, in frequency domain Green's function, what I do is normal, I take G equal to 1 upon R plus we can take some function H, which is basically depending on the point P and Q, where P is the point, any point in the domain, where Q is the point on the body. And if you talked about the time domain, then Green's function is can be taken as this Rankine part plus. Now, we can now assume this second function is not harmonic, in that case it is harmonic. Now, it is P Q and also it takes some parameter T and tau. Now, what is this parameter P Q T tau, that definitely we are going to discuss when you discuss the time domain panel method, but categorically this Green's function can be divided into three parts. One is Rankine. Now, Rankine Green's function can be solved in frequency domain or time domain. Already if you assume the second part is harmonic, or you can say the pulsating Green's function, but the Green's function is harmonic. So, you can call it the frequency domain Green's function, and if it is impulsive Green's function, it is called the time domain Green's function. So, now it is the same. Now, you understand this all. Now, in case of A2 we have to discretize the body as well as the free surface. In case of A1 we have to discretize the body only, and in case of higher order panel method, now you can see that these patches are really big comparison to the other two mesh, right. Okay. And this is the basic Green's integral equation we are going to discuss from the next class, and how we can solve this problem, right. And now I understand what is phi p, what is G p q and what is the S, everything. Okay. So, the idea is formulate the boundary value problem for phi, and then we find the proper Green's function. Remember this, because we are going to discuss again next class the same thing. Now, these things again need some kind of discussion that we are going to discuss in the, when you solve a practical problem. In the next class we are trying to solve a problem for a infinite domain radiation problem. That time one by one we are going to discuss all these things. Okay. Thank you.